No, you gotta, is that okay if you...
Your mic's hot.
Oh, okay.
Is that okay if you hold her?
Yeah, yeah.
Sorry. Is it working?
It's fine.
Live?
You can
Okay.
put it down.
Okay.
I'm just.
I didn't know if it was on.
We're going now. I'm
Okay.
just letting it.
Okay.
Testing 1 2. Testing 1 2.
They're office hours, and I don't really feel comfortable keeping them, so I'm donating them to your defense.
Thank you.
They are not enough for everyone.
Testing 1 2. Testing 1 2.
Testing, testing.
You give me a mic check. Just
Testing, testing, testing. 1, 2, 3.
A bit louder.
Testing, testing. 1, 2, 3. Testing, testing. Testing, testing.
Yeah,
Okay, we're all good. I can hear myself, so you guys should be able to hear it online.
yeah, I don't know why ours are so early. Is it that way every year? Or is it just this year? I mean, I wouldn't know because last year convention was messed up, and I wasn't there the years before.
By messed up, it didn't happen.
Well, there was the encampment, so they couldn't accept things up for a while.
But they had it.
No, they canceled the regular class, but then they did an event that was on campus. They didn't call us.
You got a clicker?
Yeah.
Good. All set? Okay, I think we have pretty much everybody here. So welcome everybody to join us for celebrating Daniel's thesis defense. This is the public portion of his defense. After this, we're going to grill him with many questions about his work over the last 5 years. So, you know, Daniel's work has this theme of wobbles, and it's normal as a PhD student to have a bit of a wobble during your PhD, but it's less usual to dedicate your entire PhD thesis to the theme of wobbles. And so Daniel's been doing this remarkable work trying to understand what we call transit timing variations, these interactions between planets. And he's really had an incredibly productive PhD, and even before that. So to date, he has now written, I think, 27 peer-reviewed papers, which is really astonishing for a PhD student, 6 of which he led as the first author. And I don't know if this is true as of today, but I certainly remember when I was writing your letters, you had 810 citations and H-index of 16. So this actually put you, at the time, I wrote this in the letter very clearly, you're in the top 7% of all, not just students, but people who went on to get prize fellowships. Amongst those people that get prize fellowships, Daniel's in the top 7% for number of papers and the top 4% for H-index. So truly an outstandingly productive scientist. I'm certainly going to miss him in the group. Daniel was extremely professional, mature, but also a lot of fun to have around, and we had a lot of laughs together in our group meetings. So we're going to hear now about his incredible work on Wobbles to Worlds. So please take it away.
Thank you. All right. Thanks, everyone, and thank you all for being here. I have the not so enviable task of trying to summarize the last 5 years in about 45 minutes or an hour and not keeping you far too long. I'll do my best. But as I'm going, if there are like questions or things I say that don't make sense, please stop me. Bring it up. So as David said, my thesis revolved around Wobbles. So from Wobbles to Worlds, how do we develop a framework for detecting unseen planets and moons? And throughout the time, I worked on a number of projects, which I'll try to walk through today. The first set can be classified with future injection recovery of astrometric and radial velocity observations. to search for solar system analogs. And then I worked on a project developing a code called the democratic detrender that removes stellar activity and other sources of noise from time series photometry. And then the bulk of my thesis is on these transit timing variations, these TTVs, and working on methods to differentiate between the root causes of these wobbles in planets' orbits. And if I tried to think when I was writing my applications, my postdoc applications, how do I kind of branch this all together? And there's this term that I believe Sarah Milholland coined called data-driven dynamics, which I think just kind of encompassed everything I worked on. So the idea here is how do we use data analysis techniques to help inform and constrain our dynamical simulations, these models, these integrations over much longer timescales, and then what can our dynamical integrations tell us about the data that we're seeing, and how do we really live at the intersection of those two worlds at trying to push what we can say about planetary systems and architectures and evolution. Okay, so today I'm going to go through the 7 chapters of my thesis. I'll start with an introduction. The easiest place to start when talking about exoplanets is with solar system planets. So in our own solar system, we have 8 planets. The 4 inner ones are rocky worlds. They're smaller. They're rocks, essentially, if you take it to the smallest simplification. And then the 4 outer planets are gas giants. They're much bigger. They're balls of gas. And they don't have this rocky core and mantle, and et cetera. So those are our solar system planets. How do we think about exoplanets over time? So the first exoplanet was discovered in 1995 via radial velocities by Didier Queloz and Michel Mayor. It came after 5 years or a decade of looking for exoplanets being by radial velocity observations. That was led by people like Gordon Walker and Dave Latham. And over the next decade, the majority of all observations were really these radial velocity observations. Then moving forward, we had this boom of exoplanet discovery that went along with these transit searches. So what are transits? So this transit method has been used to find the majority of known exoplanets to date. To quantify this, as of late April, astronomers have discovered about 6,000 exoplanets, and 4,360 of them have been found using the transit method. And there are 2 main workhorses that have really led to these discoveries. There's the Kepler and K2 mission using the Kepler Space Telescope, which ran from 2009 to 2018. And then there's the TESS mission, which started in 2018 and continues to this day. And these 2 missions contributed to the bulk of these transit exoplanet discoveries. So Kepler observed about 500,000 stars, discovered about 3,000 exoplanets with additional 2,000 candidates by only observing about 0.25% of the sky, but observing it very deep. So they could observe faint stars in this small field of view. Whereas the TESS mission adopted the opposite approach. It looked around almost the entire sky, but only at our brightest and most nearby stars. So launched in 2018, observed around 200,000 stars. Just so far as discovered, confirmed 623 planets, but there's an additional almost 8,000 candidates that TESS has identified. And to visualize what this looks like, the TESS observing window follows a pattern like this. So it observes in 27-day-long periods and kind of tiles the night sky over time. And to compare, in yellow up there, up top is the standard Kepler field. The K2 mission was essentially a way to save the Kepler Space Telescope after 2 of the reaction wheels failed, and that's where you see these yellow tiles around the ecliptic. They were able to extend the lifetime of Kepler by another 5 years or so by changing the viewing of where Kepler was looking. So transits are really helpful, but as a lot of our data comes from transits, it's also important to understand what are the drawbacks of the transit method. So when might we not observe a planet via transits? So first of all, there's a low probability of the planet being properly aligned. For a transit, we're talking about eclipses. So we're looking at a distant star, and the planet is passing in front of that star relative to us. And we're looking for a decrease in the amount of light that star is emitting. So you can imagine that if a planet is oriented like this around its star, we're over there, and we're looking at the star system, we would see that the planet is blocking some of the light over time. However, if we rotate this orbit here will never pass in front of the Earth relative to us. And so we can see that there's a favored orientation at which we would observe a planet via the transit method. We can also quantify this. So the Earth-like planets around a sun-like star, for neighboring stars, if they were trying to observe the Earth as a transiting planet, there's about a 0.5% transit probability. And we could also say that the larger the planet's orbit, so the further the planet is from the star, the lower that transit probability becomes. So therefore, transits are more sensitive to close-in planets. And additionally, it's harder to detect smaller planets. So that's because the transit depth, the amount of light that is blocked by the star, scales with the planet radius. So the bigger the planet, the more light it blocks. And so with a certain sensitivity of a telescope, you're only able to observe down to a certain size planet. We can see this here, so we'd imagine if we're looking at the star, on the right is what the brightness might look like over time. If we have a planet that's this big, it'd block this amount of light, 4 times as big, it'd block 4 times the amount of the light. And so if our sensitivity threshold was somewhere in between these two curves, we'd be able to detect this planet, but not this planet. And we can see that also in the data. So here is all of the known exoplanets. On the y-axis is their mass. On the x-axis is their orbital period, so how far they are from the star. And you can see that there's a bias, there's a cutoff to closer in planets and planets above some certain minimum size. And I've also plotted here where the 8 solar system planets are. So all of the transit discoveries are in blue, all the radial velocity discoveries are in red, and then other discoveries are in a lighter frame of red. What's interesting, though, is due to this bias to closer in planets, nearly 95% of planets discovered via the transit method have orbital periods that are shorter than that of Mercury. So if we go back to our map of the solar system, we could say that our exoplanet transit sensitivity regime is somewhere in this region around other stars. If we zoom in on that region, we can ask the question, what are the masses? What are the typical masses we find, size of the planets? And interestingly, the most common planets that we find are so-called super-Earths, so planets bigger than Earth, or sub-Neptunes, planets smaller than Neptune. We don't know exactly what's the makeup of these. Some of them are likely these scaled-up rocky worlds. Some of them are likely scaled-down gas giants. What's really interesting is that we find so many of these planets that we don't have any in our own solar system. Okay, so that's kind of setting the scale, the stage of where my thesis existed or was motivated by. But we wanted to ask the question, how can we look for other worlds in our transit data? So imagine there are other planets out beyond our sensitivity regime. Is there a way that we can try to find them with the data that we have? And so we can imagine that other planets in the stellar system, or a moon orbiting that planet, would also gravitationally interact with our observed transiting planet. And so using our detections of these wobbles, of these small fluctuations in the planet's orbit, we can try to find these other planets, maybe Earths, Jupiters, even a moon around the planet that we see. So what might this look like? So here's what a planet and a moon orbiting a star might look like. You see there are these quick, rapid fluctuations as they orbit the star. But remember that our observations are just a transit over here. And so what you see is that the transit time shifts. So here the transit occurs late due to the presence of the moon. And similarly, if we have 2 planets orbiting a star, one of them isn't transiting, it would also induce a gravitational interaction, and we could find that it would create a similar TTV, transit time variation, of delay in when the transit time occurs. So what else can we say about TTVs? They're periodic signals, which means that they repeat. They have some sine-like function, and we can define their TTV period as how long it takes for the signal to repeat. So that's the period of the TTV, and the amplitude of the TTV is how long, how late or early are these transit times. We can also say that TTVs are ubiquitous in our data set. So if you look at the Kepler data, of about 2,600 Kepler objects of interest. So these are planet candidates in the Kepler data set. 70% of them strongly favor a TTV model over a model without any presence of these variations. And many of these TTVs have amplitudes that are compatible both with planets and moons. And with our current data, we should be sensitive to solar system analogous exoplanets and moons. So this is kind of a ripe data set to try to study. Okay, moving on to our first project. This project, we developed this code called the democratic detrender. When I started working with David 4 years ago, he said, why don't you take the year and do a project we'll call Tooling Up Daniel. So instead of just diving into the data, why don't we take some time to actually develop the tools and the skills and the background that you can then use throughout your PhD and throughout your career. And that resulted in this project. So what's the motivation here? I've spent the last 20 or so minutes telling you how exoplanet transit time series data looks like this, right? Well, in reality, it looks nothing like that. This is more like what the data would look like. So before we can analyze our transit data, we have to move all of that other signal. So what's causing this? In reality, these observations come from space telescopes typically. And so there's a combination of data and noise in our observations, which includes detector noise, stellar activity, so the star itself is varying. The spacecraft might move or get kicked. There's instrumental issues. There could be telescope variations that could be observed on a different pixel. And then lastly, we have our transit. And so when we sum up all of these factors, we get our raw light curve. And the process of removing all of that activity from the light curve is called detrending. It's removing this like nuisance signal from our data. And it's become increasingly important with millions of light curves presented to the community by TESS and Kepler, as well as Kurot and KOPS, and in the future there'll be more space telescopes that'll continue to do this. And so our ability to remove this signal is really critical in studying transit data and eventually TTVs. This data's been here forever. Why isn't this problem solved? There's been extensive work to develop computationally efficient and precise and accurate detrending models. Here's a non-exhaustive list of different papers that present novel detrending methods. And the reason that there are so many of them is that all of these models are inherently imperfect. There's no way to accurately and completely model all of the activity in the star. And so all these different models prioritize different things in order to try to remove as much signal as possible, as much noise as possible without contaminating the signal of this planet. So how can we mitigate this model dependency? And so we adopted this approach that is influenced by machine learning methods, where oftentimes you don't take a single loss function or a single method in these neural networks, but instead you adopt a number of them, and then you take like the median value of this solution. And so similarly, what we can do here is we can take a light curve, run a number of detrending models, say we run 4 in this case. Then what we want to do is we want to test that the model fits the data. So we can see in this light curve here, our model adds on additional noise. And so we'd remove this. It's not a good fit from our data set. We're left with a number here we call M, 3 surviving models. We then can look at our individually detrended light curves and eventually do this ensemble step where we take the median value of each of the detrended solutions, each of these individual model solutions, to combine them into our final model. And we also inflate the uncertainties by how different the models are at each point. So imagine all 3 of the models agree very closely on a single point. We're more confident that that's a good fit, whereas if there's a big variance between them, we'd inflate the uncertainty for that single point. And so this is what it looks like run on data sets. This is Kepler 1519b. And here are 8 detrended models fit to the data. Even though they all probably look relatively flat when we run our white noise check on this data set, we find that a number of them are actually not consistent with white noise, with flat lines. We remove them from our system, from our final model, and then we get our final ensemble detrended solution. So this is called the democratic detrender because we allow our models to vote. And it was published in this, or it's submitted to the AAS journals, and it's live on this GitHub repo. Moving on to a project that we coined Not So Fast Kepler 1513. But before I get there, I have to motivate what that means, why we're talking about fast TTVs. So this goes back to this idea of this exomoon corridor. And to understand that, we need to think about planet-moon interaction. So we observe planetary transits every PT, the period of the transiting planet. But a moon orbits its planet much quicker than the transit of the planet around the star. It's by definition of where the gravitational stability is between the planets, the moon, and the star. And so our moon will wobble our planet with a period much shorter than that of our transit. Therefore, we'll observe an alias of the TTV period. And you've all see aliases all the time. If you're driving down the highway, you look at a car wheel moving really quick, our eye's frame rate is not fast enough to detect the motion of that wheel until it locks on to a slower period. Sometimes it even looks like it's going backward. This is a frame rate issue. So this is this idea of aliasing. So similarly, for moon-planet TTVs, so we're looking at the TTV of a planet caused by a moon. In gray is what the true TTV would look like. In black is where our observations are made. And if we were to fit a model to this black data point, even though there's this true inherent faster signal, we would fit to this slower period signal. So that's this alias effect. And if you look at what that aliasing will do, 50% of the time, these alias TTV periods will be between 2, which is the minimum recoverable TTV period, and 4 times the period of the transiting planet. And that's just because there's a bias to stack up closest to the minimum possible observable period. And so here, in this 2020 paper, David plotted where we imagined our density of aliased exomoons to induce TTVs versus a catalog of known two-planet TTV systems. So systems where we know that there's this transit timing variation and we know that it's caused by a neighboring planet. And what we find is that TTVs in this exomoon corridor, so in this between 2 to 4 times the period of the transiting planet, they're rarely contaminated by known planet-planet TTVs at about the 1% level. So 1% of these systems in the Haddon Lithic 2017 catalog were in this exomoon corridor as well. So this motivated us to search this corridor to look for possible new moons. In this paper in 2023, we did just that. We started with the same Hoaxer catalog that I was talking about before, and we downsampled to our best possible systems. And one system particularly stood out. It was Kepler 1513b. It is a gas giant, so something a little smaller than Jupiter on a 160-day orbit. And we wanted to ask the question, try to answer the question, is the unseen companion to Kepler 1513b a planet or a moon? And so this is what our data looked like after the detrending. In black is our transit fit to the data, and here's all of our different data sets. In purple is the Kepler data, which you can see is by far the lowest noise. In green is TESS, which luckily just happened to be observing in the correct window during one of these transits about a decade later. And in blue, orange, and red are 3 ground-based facilities that we're able to get a follow-up observation with collaborations with colleagues through the TESS follow-up program. Okay, so let's look at what the TTVs look like. If we looked originally at the first 8 transits from Kepler, we see in black what the TTV is. It's the observed minus linear fit value. And we can see that you see this quick TTV, this fast wobble with a period of about 2.6 times the period of the transiting planet. In blue is our best fit to a moon model, and in red is our best fit to a planet-planet interaction model. But we obtain these follow-up observations a decade later, and we add them to our data set. We find that there's a longer-term trend that was previously undetectable because Kepler didn't have a sufficient baseline. And so here's our TESS observation, and here's the next ground-based observation. And you can see that our planet-planet solution, the solution in red, can trace out this long period trend, whereas a single moon model, which essentially creates a TTV signal that looks like a sinusoid, can only trace a flat line and is unable to account for this early TTV at epoch 30. Okay, so we're looking at this data. This follow-up kind of kills this fast TTV exomoon corridor solution. we realize that's no moon. And instead, that Kepler 1513c is likely a Saturn mass planet that's about 5% outside a 5-to-1 period ratio with an already known planet. There are additional targets that we're excited about in the exomoon corridor. One particular is KY 3762b, which is actually Kepler 1519b. So you saw the light curve before. It's a different name, but the same system. It's a 10 Earth radius gas giant at about 240 days. Currently, the short TTV period is dominated by the single observation. And so we're trying to obtain follow-up observations to try to determine similarly whether this short period signal remains. We've already obtained 2 ground-based follow-up observations with the same tests, TFOP, subgroup 1 collaborations, and we're going to hope to continue to do so in the future. Okay, so now we looked at this single system. We had this case study, and we wanted to now ask the question, what does the whole orbital landscape of planet-planet TTVs look like? How can we try to get a sense of what this landscape looks like in all? So to start, it's important to think about how an observer would process the data if they're observing a transiting system. So imagine, first of all, that you're observing a system, and we know of 2 planets in the system, and we know where those periods are. They're both transiting planets. We know what the period is. It's very straightforward. Use our analytic formula, which I'll show in a second, to go from the period of the transiting planet and the period of the perturbing planet and predict what the period of the TTV is. However, the inverse is not true. So if we know that there's a transiting planet, we don't know that there's this outer planet there, but we see some variation. It's not straightforward. It's very degenerate to go from a transit period and a TTV period and predict the period of that perturbing planet. To understand this, we could look at our analytic formulae. So the 2 driving forces of planet-planet interactions on a TTV timescale are near mean motion resonance, induced superperiods. So what are those words? Resonance is when you're near an integer ratio of each other. So imagine your periods are in a ratio of 2-to-1 or 3-to-1 or 4-to-1 or somewhere near that. And that's what this J and K value are. So a 2-to-1 mean motion resonance, you'd expect a J to be 2 and the K to be 1. And the period you'd observe for that TTV would be this super period. I'll also just point out most multi-planet systems that we know about are in the low eccentricity regime. This is true via a number of different types of observations. And in the low eccentricity regime, we expect first order resonances to dominate. So that's resonances that are like 2-to-1, 3-to-2, 4-to-5, 5-to-6, so on and so forth, rather than like 1-to-3, 1-to-5. We expect these low first order resonances to be the dominant signal in the low eccentricity regime. The second effect that dominates planet-planet TTVs are conjunction-induced TTVs. So these are the closest pass-bys of a planet. So imagine 2 planets are orbiting their star, and we're talking about these moments where they have these close pass-bys, because that induces a kick in the orbit. And these are sometimes called chopping signals, because how they look on the TTV data set is like there's a long period signal, and then there's like a chop on top of it at these conjunction points. Okay, so moving on to the plot that I've stared at for the last 3 years, and everyone in the astro department is very tired of looking at. On the x-axis, I'm going to plot the period ratio of the planets. So if you go beyond 1, we're talking about a perturbing planet that's more distant than our transiting planet. If you go inside 1, you're talking about a perturbing planet that's internal to our transiting planet. And on the y-axis is the TTV period normalized by the period of the transiting planet. And if we plot some of these first order resonances, first order super periods, as well as the synodic period, this conjunction-induced period right here, we can see straight off the bat where this inversion problem happens. So if we know the period of the transiting planet and we know the period of the perturbing planet, that's equivalent of having a vertical line across this graph. So if we slide a vertical line anywhere in this graph, there's only a single intersection point. And that at that single intersection point is where that TTV period would live. Inversely, if we have a horizontal line across this graph, because we know there's a transiting planet, we know there's a TTV period, but we don't know where that perturbing planet is, our horizontal line, as it scans across this graph, has many intersection points everywhere. So that's this degeneracy. At any of those intersections is where a perturbing planet could be. And I'll just add on this graph, here is where that exomoon corridor would live, so right between 2 to 4 times the period of the transiting planet. We can test this analytic solution via numerical simulations. There's a code called TTV fast that was written by Deck et al. In 2014 that allows us to simulate how planet interactions would cause TTVs. And so what we did is we simulated a number of 2-planet systems with a range of planetary masses, a range of planetary periods, eccentricities, inclinations, and so on and so forth. And then we fit to the output data set and ask the question, what is the period of this TTV signal? And then we plot each of these as individual dots on the line. So even though it looks like there's a smooth black curve through some of these plates, it's actually, each of them are individual dots of about this size that just look like they become a line because they stack on top of each other. I'll just add one other thing to this graph, and then I'm going to label these curves as well. So the next plot I show is going to be a little bit overwhelming, I'm just warning you. But the nearby orbits become chaotic by this Deck et al. Criteria. So if the period of the 2 planets is less than this value, where this epsilon is the sum of the planet masses in the units of the stellar mass, then the system will be chaotic. And so if we had 2 Earths, anything within this regime would be chaotic over short timescales. If we had 2 planets of Jupiter mass, then they become chaotic over this timescales. And what I'm plotting here is the same exact plot, except now I've color-coded each of these circus tenths, super periods, by what resonance is actually dominating here. So everything inside 1 you can explain with an alias of the 2 to 1, except this peak is a 3 to 2, and same as this one. And outside, you have similarly first order resonances, but instead it's 2 to 3, 3 to 4, 4 to 5, so on and so forth. And so what we suggested with this paper is, instead of fitting blindly over the whole parameter space, what if you fit a number of models in each of these possible regimes, and then you can get a solution for each of the possible planet periods and compare them. And so to kind of draw this out a little bit more specifically, imagine we find a transiting planet with a period equal to 10 times the period of the transiting planet, with this horizontal line across here. If you follow standard methods, what we would typically do is just fit an uninformed prior, meaning we just fit over any possible perturbing planet because we have no reason to expect it to live in one place or another. If we were to do that, what would likely happen is we would converge to a single solution. Actually, not what would likely happen. What would definitely happen is we would converge to a single solution. So find a single place, a single intersection point on this graph, and tell us that's our answer, without knowing about all of these other possibilities. And so instead, what we propose to do is we now know where those intersection points are, so basically test around those regimes in order to fully sample this full parameter space. Yes, we now have a way to understand how to fully traverse this orbital landscape of planet-planet TTVs. Okay, now to the exoplanet edge of planet-planet TTVs. So if you look at this graph, the keen observer might have noticed that there's 2 things that stick out, and that's these 2 lines here. And so about 2.5 years ago, David and I, or 3 years ago, David and I saw this for the first time, and were very confused. We didn't know what was causing it. We thought maybe we were doing something wrong in our simulations, and it's kind of sent us down a rabbit hole of trying to understand what could be causing these signals. Is it physical? How can we understand it? And thanks a lot to some of my collaborators who I think might be on this live stream, especially Eric Agel and David Nesvorny, real hardcore dynamicists in the field who helped me walk through this challenge. Okay, so if we look at these 2 lines, I'll point out that the TTV period is equal to the period of the perturbing planet on this upper line, and equal to the period of the perturbing planet over 2 on that lower line. So how can we explain it? What's causing these edges? First, let's think about conjunction-induced TTVs. So these TTVs that are caused by these close pass-bys of the 2 planets. And as I said before, we'd expect them to occur at a period of that synodic period, which is when the planets have the closest pass-by, you get one pass-through of the TTV curve. But We don't observe the full orbit of our transiting planet. We only observe the transits. So we can ask the question of what do TTVs look like caused by these conjunction effects for a distant perturber during transits. And so what I've done here is I'm walking through a number of transits of this inner planet. And on the bottom line is that black curve is that synodic period. But I'm pausing it at each time that our transiting planet passes in front of our observer, as marked by the eye. And what you'll see once we walk out through a full orbit of this outer planet is that even though there's this faster TTV period, we again observe an alias. But what's interesting here is that the alias is by definition going to be equal to the period of that outer planet. And that's because for the first half of the outer planet's orbit, it induces early TTVs, whereas on the second half, it induces late TTVs. And so we can then explain this upper edge by an alias of the conjunction, alias of this synodic period. We still have this lower edge. So how do we explain that? For that, we have to go to tides. So on Earth, the way that we commonly think of tides is the Earth rotating under the moon's gravitational pull. Twice a day, you get a high tide and a low tide as induced by the moon. The oceans are pulled, out and back due to the moon's gravitational pull. So similar to the stretching of the Earth's ocean, if we have an inner planet and a very distant outer planet, this outer planet can induce tidal variation to the inner planet's orbit itself. And so it elongates the orbit. And so if we now step through what that looks like as the outer planet goes through a full orbit, you see that the inner planet will have this wobble with a period that's actually, again, equal to the period of the outer planet. But because there's this symmetry, because there's a symmetry in both axes, what we would observe is actually a period equal to half the period of this perturbing planet. We wouldn't be able to tell that this is different than this. And so thus we can explain this lower edge by the rotating tidal interactions of the two planets. So how can we use this exoplanet edge? First of all, the reason we call it an edge is because we think it's this limit below which we don't expect any planet-planet interaction to induce an observable TTV. So therefore, any planet that falls below this lower line is indicative of that there's extra mass in the system. So there's some other planet we don't know about, or maybe a moon. Presence of an unseen world. And so what we did is we went back to this Hoaxer catalog, this Kepler data set, and we looked at all 2-planet systems. And for those 2-planet systems, we found all the planets that had convincing TTVs. And then we asked the question, where do they fall on this diagram? And so in kind of salmon are the 52 KOIs that have a period greater than edge-like. So they're likely these super periods that fall on one of these circus tents. In blue is what we think are likely these edge-like interactions. So there's 32 of these systems that fall in or around the edges. And then in maroon are 13 KOIs that have a TTV below this edge. And so for these 13 systems, we believe that there's likely additional mass in the system. And similar to what we did for Kepler 1519 and Kepler 1513, we hope to get follow-up ground-based observations and try to learn more about what could be causing these anomalously fast TTVs. Now, the second thing we could hope to do with this exoplanet edge is actually look for distant perturbers in single planet systems that are along this edge. So how would this work? So if we go back to our diagram before, now all I've done is I've increased the x-axis out to period ratios of 100. In this case, imagine you're an observer. You know that there's a single planet in the system, and you see a TTV variation. So maybe you get ground-based observations, and you're able to rule out any planet within a period ratio of 4 of our inner planet. So we now know that there's no planet here. And now say you observe a TTV period that's something less than 6. For anywhere in this regime, unlike the rest of the parameter space, instead of having like 20 solutions of where you could overlap with this line, we now have 2 possibilities. And so we can look specifically, you can target for these distant planets at those precise period ratios and hope to find some of these distant planets that are typically very difficult to find. And there's a natural overlap here with Gaia and DR4 astrometry, which I will talk about here in my last chapter. Okay, so what are the current exoplanet detection limits? We've been talking so far about transits and TTVs. If we have a star here, we call this the habitable zone, which is where liquid water can exist. Transits, for the most part, exist kind of out maybe to the habitable zone. TTVs could maybe help us get further out, but it becomes more complicated. There are multiple solutions. So how else can we fill in this gap? First possibility is using radio velocities. So radio velocities look for wobbles again, but now we're talking about wobbles of the star. So if you look at the spectra of a star, which means a wavelength-specific observation, when a planet orbits around the star, it pulls it forward and back due to the motion around the center of mass of the system. And so the spectra, this wavelength-specific observations, will shift due to the gravitational influence of this planet. So we see red shifts when the wavelength is stretched, blue shifts when it's collapsed, kind of similar to it's like a Doppler effect. So if you've heard a car horn on a road, it changes in pitch as it passes you. So that's what we're looking for in radio velocity methods. And RVs are sensitive, can be sensitive out to more distant orbits, but you have to observe it for a really long and a really targeted observation framework. And additionally, there's astrometry. So astrometric observations, again, wobbles, but about the star relative to other stars. So now we're looking in a different axis. So instead of looking at the star's motion like this, we're looking at its motion in the plane perpendicular to you versus other stars. And so we can see in this animation here, we're tracking as this central star how it varies compared to these other three stars due, again, to the presence of this inner planet. And so with astrometric observations, as opposed to radio velocities and transits that are more sensitive to inner planets, you're actually more sensitive to outer planets. So astrometry is better at finding distant planets than close-in planets. The signal gets larger for a more distant planet. And with Gaia, there's hope that we could find thousands of outer gas giants. Gaia is a European space telescope that's been observing for the last decade or so. I think it recently shut down, but there are future data releases. So in 2026, there'll be data release 4, which will include the raw astrometric data for the first 5.5 years of the mission, and then in the coming years, there'll be more complete catalogs of the Gaia data. And so we can ask, what will Gaia be sensitive to? And so if we take Gaia's nominal observing plan, this is for stars within 50 parsecs. You can think there's about tens of thousands of sun-like or slightly smaller, bigger stars. And this black curve traces out what Gaia should be sensitive to, assuming 138 observations, which is what the average will be over the entire 10-year Gaia lifetime. So this lower curve is around a star that's 1/10 the mass of the sun. This upper curve is around a star that's the mass of the sun. You can see that it'll start to really fill in this regime of space that we currently are not sensitive to. Additionally, though, hopefully soon, Roman will launch the Nancy Grace Roman Space Telescope, which is a telescope, an instrument that has a 0.28 square degree field of view, so I think 100 times larger than Hubble, but a 2.4 meter primary lens, so the same size as Hubble. So imagine if Hubble could observe 100 times more at every single observation. So this is a graphic of that. This is what the Hubble observing window would be compared to Roman. Roman is basically very close to ready to launch. I think on the current NASA proposed budget, it would not launch, so we'll see. Hopefully Roman will launch soon. It was previously called W First. So this Roman astrometry working group in 2019 said that for bright nearby stars, so closer than 10 parsecs, slightly closer than this plot I showed before, it should be able to detect Earth analogs, more distant planets with periods up to greater than 10 years by adding in Gaia data as well, and have an astrometric precision of about 1 to 10 microarc seconds. If you don't understand just how ridiculous that is, that's like having a telescope in California and you could observe the width of a hair in New York for the scaling. So it's crazy. And if we add in Roman here, so this is again around 50 parsec stars, assume about 4 observations a year around a critical, say there's some star that we're particularly interested in, you get 4 observations a year for the 10-year lifetime. You can see that Roman observes, increases our ability to detect some of these smaller planets. If we add in here where our solar system planets are, you can see it's still slightly below. But if we go to 10 parsecs, where there's more like tens to hundreds of stars that are possible, you can start to get into the regime where we might be able to might be sensitive to Earth-like planets. Okay, so that's the astrometric side of things. On the radio velocity side of things, there's an experiment called the terra hunting experiment, which will get 10 years of daily radio velocity observations of at least 40 bright and nearby G and K dwarfs, so sun-like stars, think. And they're the 40 of the brightest and most nearby of those stars, with the goal of searching for Earth twins in the habitable zone. In this simulation paper in 2018, Hall et al. Showed that Earth twins would be detectable in the terra hunting data set. And according to their website, they expect first light before the end of 2025. When I started this project, they expected first light in 2022. I'm not sure exactly when it'll happen, but it'll be coming soon. So RV and astrometry are particularly well suited to work together, and there's a number of reasons for that. First of all, radio velocity is one-dimensional function of time. So we see the star moving back and forth due to the planet, and so there's a mass inclination degeneracy. That means we don't know whether there's a small object right here or a bigger object right here that's pulling it up and down like that, but we only see this component of the velocity. So we can only determine the minimum mass of the planet. Whereas astrometry is a two-dimensional function of time. We see the motion against this full plane. And so we can determine the actual mass of a planet that maybe radio velocity can discover, but astrometry allows us to break that inclination degeneracy. And secondly, as I said before, radio velocities, like transits, are more sensitive to closer in planets. So the radio velocity signal scales with period to the -1/3, whereas the astrometric signal is more sensitive to further out planets. Astrometry scales with period to the 2/3. And so the question that we sought out on this project, which I got to work on as a first-year project, which at Columbia you do a first-year project with a different advisor and then a second-year project with a different advisor. So I got to work on a completely different thing, and this was primarily with Ruth Angus and David Spergel at the CCA and the museum, is we asked the question, can we use this 25 years of Gaia and Roman astrometry in combination with the 10 years of terra hunting RVs to look for solar system analogs? And what we define as a solar system analog is an exoplanet system with an Earth analog and a cool gas giant, so a Jupiter-like or Saturn-like planet around a sun-like star. So we're not looking really at this, we're looking at this. And the reason for that is in our own solar system, Jupiter and Saturn are so much more massive than everything else, they really dominate the formation and the evolution, we think, of how our solar system came to be. And so as a first step in looking for solar system-like stellar systems out there, you could naturally look for Jupiters, Saturns with an inner Earth. So what do we have the ability to really change? This Gaia catalog will exist. This terra hunting catalog will exist. And so the real question is, how can Roman help? How much will Roman help? How much can Roman help? So what we did is we tested several different possible observing approaches. We first asked, what if there's no Roman observations? So do we actually need to invest this expensive telescope time? We tested whether single observation precision is 5 or 10 microarcseconds. If you remember from the working group study, they said it would be down to 1 to 10 microarcseconds. So we adopted a little bit of a conservative approach here. And then we asked, what if we observe 4 times per year for either 5 years or 10 years? How much does the baseline of the observations matter? And without going too much into how our simulation show, what I'll show you here is the results from Earth and Jupiter injection recovery. So what we do is we simulate the data, we throw in an Earth and a Jupiter, we simulate what the radio velocity data will look from terra hunting, as well as the astrometry from Gaia and Roman, and then we fit to the data as if we're observers looking for these systems. And so on the upper row is period, the recovered period. On the bottom row is the recovered mass. On the left side, you're looking at the actual period recovered versus the true period that was injected. So this is for Jupiter, this is for the Earth. And then same thing here with the masses. Here what you're looking at is the fractional period uncertainty. So how big are these error bars essentially? And here what we're doing is at each line is a different one of these possible observing plans with Roman. So the top line is no Roman, and then we go to a more intensive and a better Roman observing capabilities as you move down this plot. And essentially what we take away from our studies is that terror hunting radial velocities and Gaia astrometry together can detect Earth-like and cool gas giant-like planets around bright stars within 10 parsecs. So that's basically the fact that even with just Gaia, we're recovering the correct mass and period for these planets. But including Roman astrometry improves this precision for cool gas giants in mass and period by factors of 10 and 4 respectively. So we get much more precise periods and more precise masses by adding in Roman. For the gas giant specifically, for the Earths, we're really anchored by those terror hunting observations, so you don't get much improvements there. And such a survey could provide insight into the prevalence of solar system analogs, these exoplanet architectures reminiscent of the mass and orbital hierarchy of our solar system. Okay, so conclusions and future work. Hopefully, I've convinced you that using this data-driven dynamics approach is a good way to live at this intersection of data analysis, simulations, and really push to the forefront of understanding of exoplanet formation, evolution, orbital configurations. So what's next? One of the things I love, and I've come to love about doing astronomy, is I find that like every time you do a project, there's just a number of other ideas that come from it. And so here are some of the things that we're thinking about now. In the TTV model selection world, we've created this orbital map for planet-planet TTVs, but we want to test it. We want to see how well can we actually recover planets using this system. We don't want to just give a tool to the community without knowing that it's effective. We want to do these exoplanet edge follow-up studies, so following up these anomalously fast systems, looking for other worlds in those systems. We want to investigate the whole population of Kepler TTVs, trying to understand at the statistical level, at the large population level, if we can make any estimates on the likelihood for planet-planet interactions to dominate versus planet-moon interactions. Can we say anything about what the population might look like? And then lastly, I spoke about Kepler for the majority of this talk, mostly because while the test data exists, there's no test TTV catalog like the Kepler catalogs. There's no catalog of all of the transit timings of test systems. And so integrating tests in the future would be a really promising way to continue these pursuits. And then integrating future astrometric observations is what I think a lot of my next couple of years will be focused on. So Gaia, this European Space Telescope, will have data release 4 in mid-2026. We'll have this influx of 5.5 years of astrometric data, and I'm really excited to try to look at that and see what we can learn about these cool gas giants in the Gaia data set. Okay, so that's the science portion of my talk. But because you're all here and because I'm at the front, I'm also going to spend a little time thanking people and going through a bit of a personal journey. So here is a Mars passport I made for myself when I was 7 years old. This is what I've wanted to do since before I knew what it meant to do this. Apart from maybe 3 years in there where I thought I was going to be Allen Iverson, but that didn't happen either. And I'm really I'm so grateful for this privilege and this opportunity to get to study and think about these things that I've been the most excited about for really as long as I can remember. And there's so many people that I owe that to. First and foremost, my parents and my brother, who I think is outside with his daughter, and his lovely wife, Ezgi, who've given me the support system to get through all of this. I'm very honored to see so many family and friends here as well. It's really moving. As I've gone through this journey to here, it's not all been like straightforward as life goes. And I really was so lucky outside of just that family and friend structure to have like really incredible science mentors. So I think some of them are here and on Zoom. So Mr. Gruber was my 9th grade science teacher, who was one of the first people who really saw this light in me and encouraged me, as well as people like Stefan Alexander and David Spergel, and some of these early interactions. Tim Halpin-Healy, who helped me with a Michelson-Morley interferometry project in high school. And I really was just so lucky to have these really early interactions. And then when I got to college, I went to undergrad at MIT, and there were ups and downs academically. And I was really fortunate again to find really supportive mentors. So I think Paul Schechter's on this link, hopefully, but I started working with him on a project my junior year, and he really like showed me what it meant to own a scientific project from start to finish. And I just remember like having so much fun getting to like see what that scientific question and methodology and practice, how that worked. And then my senior year at MIT, I took an exoplanet class with Sarah Seeger, and that really awoke this desire to do exoplanet-related science, which I've pursued since. Coming out of undergrad, I had to apply 3 times before I got into grad school, and that's like the best accident that ever happened, because I got to work for 2 years with Dave Latham and the rest of the test team, and I really just grew so much as a person and as a scientist, and I'm so grateful again to Dave and to the rest of that team that encouraged me and allowed me to continue growing in this space. And I'm sure I'm forgetting a number of amazing mentors who've been along the way. I think Chris Jones, one of my math teachers in my school, I think he's also on this link, so thank you also. But I say that because I know that a lot of those opportunities, while maybe I like jumped at them and took advantage of them, were in part made possible because I lived in a world where I could interact with really good teachers and really good professors. And so one of the things that I've been most proud of in my time in grad school is working with these high school outreach programs. And so this is a program up in Boston called the Harvard MIT Science Research Mentoring Program. These are 10 students who participated in the program 3 years ago. So when I started at Columbia, the program went remote with COVID, and I was able to stay involved, and I stayed involved through the end of last year. And then this year we started a program at Columbia, thanks a lot to the support of this NOLT program we have in the department, and David Helfand, and Ruth Angus, and Rashmi Mukherjee, and other faculty who really gave me allowed me to try to do this crazy idea, and all of the grad students who mentored and made this possible. And it's really been so fun to get to work with high school students and try to provide some of those experiences that were so transformational for me. And I have some pictures from my time at Columbia. So here's MDM. I bet Ben can guess what's coming next. Is me watching the Eagles Super Bowl at MDM. This is the one they lost, so it was a very sad night. Here's me. I got to go to New Zealand and talk at Extreme Solar Systems. David Nesvoni dragged me caving after that. Matt, another grad student in the department, took me and Ben up Mount Baker. This is me after I submitted my 51 PEG fellowship and collapsed in Ben's office. This is at a conference in Tokyo. And lastly, picture with David at an outreach event a couple weeks ago. I'm so grateful for the time I got to spend working with David. He's, anyone on YouTube can attest that he's so inspiring and is able to really communicate science at such a good level. And he's allowed me and encouraged me to be creative and bold with the topics I work on. And I've really just learned so much and enjoyed so much working with you. So I'm forever grateful for you as well. And I want to end on a final note on people who are not able to be here today. So these are my 4 grandparents. Dorit, Mordecai, Dorothy, and Albert. They were all immigrants. They were all essentially refugees who fled their home countries, Iraq, Iran, Russia, and Ukraine. And I'm here today on the back of their strength and their hard work. But I'm also here on the back of of other people's empathy and willingness to accept others. And I think in this world today that has become more and more polar and othering, I just want to end on a note of like, people come from all different backgrounds and life, and those differences are really special. And the more that I've gotten to study exoplanets, the more I've come to appreciate the planet that we're on. And so I think that the world would be a better place if we could all have more empathy for that. And I actually realized I was going to click one more time. I do have to add Carmel Delaney to this slide. So Carmel is Mike's mom and Chris's wife, who was killed a couple months ago, and she was the most beautiful person who embodied all of these things, and she saw the best in everyone, and had an impact on everyone's life around her, including me. She was instrumental in me getting into the college that I went to and pushing me, and I'll miss her conversations and her support dearly. But yeah, I wanted to also mention Carmel as well. So on that note, I'll conclude, and thank you all for listening.
All right, we have time for some questions. People on the committee, please, apart from clarification, save your questions. Everyone else, please ask away if you're okay.
So on the topic of the democratic detrender, I'm curious. I imagine a lot of these different detrender models have kind of been built on one another or built for kind of different purposes. I'm curious if you've seen some of these different models be more or less accurate relative to one another or towards other kind of observations, and if there's like a way to essentially incorporate that into how the voting scheme works. I know it's not right now. It's
Yeah.
just one vote. Is there kind of a way that you're thinking about weighing these depending on the use case?
Yeah, that's a really good question. I'll repeat the question. So the question is, on the democratic detrender, are there certain of these detrending methods that are more favored than others, and is there a way to weigh the voting based on how you rate the ability to trend the light curve? So on the first question, you hit the nail on the head. There are certainly a number of different approaches, and they all have been built typically for a specific purpose. So there are strengths and weaknesses based on what you want to do. The way that we've built this code is that it's modular. And so we have 4 built-in detrending methods that you can run on the data out of the box. But if there's some reason you don't like one of our detrending methods, you could remove it from the voting scheme. If there's an additional method you want to add, we allow the user to pass in their own detrended light curve. We don't currently have a way to weight because I think that there's just not really a good way to rigorously determine what is a better detrending than another. Yeah, yeah. Mm-hmm.
I'm wondering with the TTV method, is there any way for more than just planet-planet interactions, like wiggles on wiggles on wiggles? And is that
Yeah.
detectable even? Or?
Yeah, so the question is for TTVs, are there possibilities for more than just planet-planet interactions or planet-moon interactions? Like, can there be wiggles on the wiggles on the wiggles, to quote Max? Yeah, so that's a really good question. I think, like with everything, you start at the simplest case. And so what we've been doing is focusing on just two planet systems, so these planet-planet interactions or planet-moon interactions. If you know a lot about the system already, you can do really, really detailed models on multiple planet systems. So TRAPPIST-1 is the best example of that, where there are these papers that TRAPPIST-1 is a 7-planet system around a really small star. And there's really good transit observations for all of the planets. And so people have been able to, using the TTV method, and study all of those, kind of that chain of interactions. But as we're trying to work in the place where we're kind of already blind, we're limiting it to our simplest case. And the assumption there then is that there is typically a dominant planet interaction, which I don't think we know yet exactly how good of an assumption that is. Yeah?
Really incredible talk, Daniel. Your plot for Kepler 1513, was it? You compare a moon-planet model versus a two-planet model. And the two-planet model curve, I was a little confused about why was it done. I don't want to make you go all the way back to the slide, but
The
it was, like,
choppiness?
really jumpy.
Yeah, so we've been talking about that a lot. I think it's a mistake how I plotted that data. The way that the TTV fast simulation works, it actually was Swift, but it's the same engine behind it, is that it gives you a single value at each transit time. And so all I've done there is connected the dots. And so because you're connecting the dots, it looks like it's linear in between that. But in reality, you presume it's some combination of multiple sine waves on top of each other. Yeah.
Okay, well, why don't we thank Daniel again? One more? Oh, we have one more? Okay.
So, sorry I didn't answer this question before, but when you think about the success in your research for the next 7 years, what is the ultimate value? Let's just say you achieve identifying many more exoplanets or exomoons through this method. What is the value for Earth, for us?
Yeah. The question was, what's the ultimate goal? What's the ultimate value of doing this type of research? So I think for everyone, it's slightly different. I think there's a number of routes you could go there. For me, I go back to the 7-year-old who made the Mars passport, and just trying to think about like the context in which our Earth and our solar system exists. I think one of the most powerful things we can hope to understand in this field in the coming years is we now know that there are a lot of other planets, but we don't really know the context with which our solar system exists. We don't know whether the solar system is really common amongst those thousands of planets or really rare. And so one of the things that I'm most excited to think about is trying to understand, once we now open up our data set with Gaia and hopefully these TTV models to some of these more distant planets, can we understand the context in which the solar system exists and get a better understanding of things on that scale.
Okay, so I'm going to close it there so we have plenty of time for the defense. So thanks to Daniel one more